Hi folks, Chris McClure here. Now we're going to talk about the central limit theorem, which is one of the bedrocks of the field of statistics, as we shall see. The central limit theorem tells us that for a population with any distribution, no matter how weird it is, the distribution of the sampling means, meaning the sampling distribution that we talked about from the previous section, approaches the normal distribution as the sample size increases. This procedure forms the foundation for estimating population parameters and hypothesis testing, as we shall see. Now, here are some assumptions. Number one, that we have a random variable x that has a distribution which may or may not be normal, but has a distribution with a mean, with the mean of mu and a standard deviation sigma. We're also going to assume that we have simple random samples of all size n, whatever n is, could be 2, could be 20, could be 2 million, but they're all the same size, n, and that these simple random samples are selected from the population. And here's this alibi here that the samples are selected so that all the possible samples of the size of the same size n have the same chance of being selected. They all have the same. That's what it means to have a simple random sample. Now, the conclusions that we can draw from the central limit theorem include that the distribution of the sample means will, as the sample size increases, approach the normal distribution with the mean mu and the standard deviation sigma, which is the population mean and the population standard deviation. We can also conclude that the mean of the sample means is the population mu, just like I said. But the standard deviation of all sample means is not just sigma, but it's sigma over the square root of n. So as you could see, that the larger the sample size, the smaller the standard deviation of that sampling distribution is going to be. Practical rules here. Samples of size larger than 30, distribution of sample means can be approximated reasonably well by a normal distribution. And the larger the sample size, the better the approximation by the normal distribution. And the second practical rule, if the original population is normally distributed, then the distribution of the sample means automatically is going to be normally distributed as well, regardless of the sample size. Now, a little bit of notation here. When you see a mu sub x bar, that means the mean of the sample means. And when you see sigma sub x bar, that means the standard deviation of the sample means. And that's just going to be the standard deviation of the population divided by the sample size, square root thereof. Sigma over square root of n. Now, sigma sub x bar, which is equal to sigma over square root of n, that's often called the standard error of the mean. So we're going to have our computer do simulations. Now we are going to produce some samples of different sizes from a normal distribution. And notice that with larger sample size 1, sample size 10, sample size 50, that the distribution in each case is normal-like. So the sampling distribution from a normal distribution is a normal distribution. If we sample from a normal distribution, if we sample from a uniform distribution with sample size 1, 10, 50, that the larger the sample size, the more normal we have the sampling distribution of the means. By the way, each dot is 7 observations. Each observation is a sample mean. If we were to sample from a U-shaped distribution like you see here, again, the larger the sample size, the more normal the distribution of the sampling is. An important point is the sample size increases, the sampling distribution of a sample means approaches a normal distribution. Again, very important. Now here's an example meant to illustrate this idea of the distribution, it's the sampling distribution of the mean. Or you could just say distribution of the means. So for this example, what we have is an elevator. Now we all know that elevators have maximum capacities. And if you have too much weight in the elevator, that elevator could either stop working, or even worse, the cable could break and everybody could plummet to their death. Not very good. So that's why we have a maximum capacity. Suppose for this elevator we have maximum capacity of 16 passengers with a combined weight of 2,500 pounds. It's either 16 pounds or 2,500 pounds. Either 16 passengers or 2,500 pounds, or both. Now, what we're going to ask is that what's the possibility that we could actually have 16 people in the car, in the elevator car, and that weight limit of 2,500 pounds is exceeded, especially if you have a bunch of football players. Well, we'll talk about it just for men in general. All right, and assuming the worst case scenario in which the passengers are all male, what are the chances that the elevator is overloaded? So suppose that we do have 16 passengers, but they're all males. What's the probability that their combined weight is over 2,500 pounds? Well, that sounds just like a normal probability calculation. And it turns out that each male has a certain probability of exceeding, whatever 2,500 divided by 16 is. Now, if you were to take 2,500 divided by 16, we can calculate the probability that, a male exceeds 1/16 of the total weight limit. Now, and then we'll do it for the whole group of 16 males. But let's go back up to here and make this note that weights for males are normally distributed with the mean of 182.9 pounds and a standard deviation of 40.8 pounds. Now we're going to calculate the probability that if you randomly select one male, that his weight is greater than 156.25 pounds. Again, 156.25 is 1/16 of 2,500. And then we'll calculate the probability that, the whole group of 16 males have a combined weight greater than 2,500 pounds, which would be the same thing as that the average weight of a sample of 16 males exceeds 156.25. So here's the calculation first to calculate the probability that one male has a weight greater than 156.25. Now, we could just convert this to a z-score, 156.25 minus the average, which is 182.9, over the standard deviation of 40.8. That z-score works out to be negative 0.65. Here's the distribution of males for their height, for their weights, with the mean of 182.9. Now we're over here at 156.25. That's our weight right there. And the area under the curve to the right represents the proportion of males with the weight of at least 156.25. What is this area under the curve? Well, we could look that up by taking a look on the table A-2 for the area to the left. Now 156.25 is 0.65 standard deviations below the mean. And looking at the table, that area to the left of negative 0.65 works out to be, 0.25, 78. So if you subtract that from 1, you get 0.7422. So one way of interpreting that is that if you were to randomly select a male, the probability that he is at least 156.25 pounds is about 0.7422. Another way of seeing that is 74.22% of the population of males have weights at least 156.25 pounds. All right. Now we're going to turn to the next piece here, and we're going to calculate the probability that if you were to randomly select 16 men and have them stand in into the elevator car, that their combined weight is at least 2,500 pounds. Meaning each individual male's weight would be whatever 2,500 divided by 16 is. 2,500 divided by 16 is 156.25. So that's a mean, and the distribution of means has the same mean as the population, but the standard deviation for the means is going to be sigma over square root of n. So that's 40.8 divided by square root of 16, which is 40.8 divided by 4, which is 10.2. So the only change between this and the previous calculation is the standard deviation, which is 10.2. And that z-score works out to be negative 2.61. Which places you right here on the distribution. And then again, looking up in the table to look up the area to the left and then subtracting from 1, we see that probability is 0.9955. As in the probability that if you were to take a sample of size 16 males, that their average weight is greater than or equal to 156.25. That has a probability of 0.9955. Very, very likely. So you know what? We need to either change the maximum number of people allowed as passengers, or maybe beef up the elevator, or maybe not make it allowed that 16 males get in the elevator at the same time. All right, so one last little piece here. Now, sigma over square root of n, that was the standard deviation that we use when we're doing probability calculations involving sample means. But if it turns out that our sample size is relatively large relative to the population, and what I mean by relatively large is greater than 5% of the population, well, then we could use this correction factor right here, where we have square root of the population size, which is capital N, minus the sample size divided by population size minus 1. So you might have to do one or two problems in the homework that uses this correction factor. Or it's an easy calculation, because in the statement of the problem, they'll tell you what the population size is and what the sample size is. So this is just an easy piece of arithmetic to calculate the square root of cap n minus n over cap n minus 1. And then multiply that by sigma over square root of n to get the standard deviation for the sample means. And that's what you'll divide by when you calculate your z-score. Okay? So with that, that's it for section 6.5. And we'll see you next time. Have a good day.